Hello, we are Group 2 and we are going to present you our jumping robot J.A.S.P.E.R. Firstly, we want to mention that a jumping robot was never achieved at Koç University, and this is why we wanted to accept the challenge and work on the project. Here you see two other jumping robots, Sandfly and Sumobot. We got more inspiration from Sumobot and used springs to generate our jumping motion. And here you see our goals. Firstly, we wanted to achieve a projectile jump and also a horizontal motion for our robot. We wanted an adjustable spring mechanism to control how much it jumps. And in our design, we had two main features we considered, durability and lightness. We also used hardware and software compatible with our physical prototype. And here you see our CAD evolution. As you can see, we've come a long way. We had to make some changes because of the material selection and some limitations of the machine shop. And most importantly, we increased our gear module, and this has helped us to make a more durable mechanism. Here you see our model evolution. As you can see, we've changed the case many times because the first one broke down, the second one was too fragile, the third one was too heavy, and at the end, we found the perfect density for our 3D printer. And also, as you can see, we had to change the gears and rack many times because they broke down or they were too small.
Here you can see an exploded view of our final CAD model. We have 21 3D printed pieces, 11 plexiglass pieces, as well as some electrical components. Here you can see our inner jumping mechanism in action. So how the mechanism works is that we have a set of gears, a rack, and two springs. We use a DC motor to drive the gears, and once the gears start turning, as you can see, the rack starts moving forwards. And this way, the springs are compressed at the back. And whenever we're ready to do the jump, all we do is trigger the system. So let's talk about the gears. We have a gear ratio of 1/24, which allows us to convert our input force of 11.18 newtons into an output force of 268.4 newtons. And here you can see our trigger mechanism in more detail. As you can see, we have a little trigger under the rack. This trigger is attached to a servo motor. And whenever we're ready to do the jumps, all we have to do is turn on the servo motor, which allows the trigger to fall forwards. And this way, we cut contact between the main driving gear and the rack. And that way, the springs are able to move backwards, and the robot is able to make the jump. This trigger mechanism is quite a novelty for us, since it allows us to make jumps whenever we want at any compression rate we want.
Now we are talking about our hardware design. As you can see in the photo, we have completed our initial design by using an Arduino microcontroller, two DC motors, a servo motor, and breadboard. One of DC motors is used to control wheels. The second one is used to control gear system, and the servo motor is used to trigger. Achieving this part was challenging for us because we are not experienced in the electronics, but in the end we achieved it. After completing it in the Arduino Uno, we transferred it into Arduino Micro. As you can see on the left side, we soldered our elements into a strip board because we wanted to achieve a more solid system to jumping. On the right side, there is a completed wheel. In that wheel, as you can see, there is a Arduino Uno and the motors, but also there is battery and a Bluetooth module. Thanks to that Bluetooth module, we can control our system from a remote controller. And this is more likely a robotic system, thanks to that. After hardware design, we are talking about mathematical model and analysis. As you can see on the graph, the first graph is jumping height versus compression rate. The maximum compression rate is around 0.1 meter, and the achieved jumping height is 0.15. This is planned one, but we have almost 0.05 meter compression right now, and the jumping is almost 0.25 meters. To achieve this height, we are controlling our system according to motor gear angle. The maximum jumping height is achieved around 5,000 motor gear angle, and we can give this input to system to achieve this height.
To talk about possible future applications of our model, we could say that this kind of a project could be used to make kids' toys, for example. And if we talk about improvements that we would make if we were to work on this project again, and if we had more time and resources, we would probably use more durable and lighter materials than the ones that we had at hand. And we would probably use springs with higher spring coefficients so that we would be able to generate more energy. And we would like to thank our professor Çağatay Başdoğan and our TAs for their support and motivation throughout the whole process. And that's all we have to say. Thank you for listening.